All right, now we got decay and growth. This is just a new formula, but everything is still plug and chug. All right, so this is A sub 0. That's an initial value that they're going to give us. Again, I think the 0 kind of makes this a little bit more specific than the P does. If you're better off seeing the P right there, feel free to do that because it's not going to make a difference. Some kind of starting amount, you could say it's a principal, no matter what you're talking about. And then on this one, it's important to notice, for some reason they're using K for the rate. I forget why that is, but maybe it throws people off the scent. But, you know, if you want to say, well, I'm going to use R for rate, feel free to do it. It doesn't matter to me. But you're going to be seeing Ks not only on the assignment, but probably the quiz. And then if we see something like this on the final, then probably there as well, okay? And then again, T is nice because it's always time in years for us. And then A of T, this is the function, the amount after some number of time. Okay, so again, this is why we know that the time is independent and the amount depends on how much time has passed. If for some reason we're looking at decay, then your rate is going to be a negative because it would be decaying, it would be losing value, which makes that exponent a negative. But that's the only value that will change. If it's growth, your rate will be positive. That's it. Oh, here we go. Certain radioactive material decays at a continuous rate of 1% per year. If the initial mass is 305 grams, how much of the mass remains after 45 years? So we have the formula right here again. So, you know, I'll go ahead and set this up again. I'm pretty much just rewriting it, right? So we got some kind of future amount of whatever substance this is. I don't know what it is. A sub 0. And there is E for Euler's constant now. We're seeing this, and we enjoy it. We love it. And this is to the power of K, so I'm going to keep K, which, again, if you want to replace that with R, that's fine. Okay, but what values did they give us? Well, they gave us the rate right here. They even said it was a rate. Remember, that's K. And so my rate at 1%, I'm just going to change that into a decimal, right? So 1%, move the decimal 2 times to the right, which would make that then 0.01. Again, that's my rate, or the K value. So I'm going to go in to my formula and replace the K right now with the exponent 0.01. That's how fast. Oh, and it's decaying, right? Yeah, don't forget that it's decaying, which means that it's going to be a negative 0.01. I know that kind of moves that decimal more above the E than up and to the right. I apologize. I should have planned better for that. In any case, they did also give us some kind of initial mass. 305 grams, that's A sub 0. That's, all right, so again, I'll show this A sub 0, that's 305. We don't need the label, but you're welcome to put it there. 305 grams of whatever this is. So I'm going to take that in the function, A sub 0, and I'm going to replace that with 305. Again, see this plug and chug business that we're doing right here? Now, even though we can't see it, there is multiplication between there. We don't have to put it there. You're welcome to put it there if it makes you feel better, but the calculator knows the difference. And then the last thing we have is time. So they said, I still got to put in my time on this one. So, all right, so T here is 45 years. So we know we're going to replace the T in the equation. That's already in years. That's nice. But I'll replace my T with 45. Okay, I'm going to put that in parentheses, although technically I believe you wouldn't have to on the calculator. So let's go and plug this in, and this will tell us A of, now it's not T anymore, remember that's 45 years. This is how much of this radioactive stuff remains after 45 years. Let's put this in. We got to talk about how to put in Euler's constant. Let's look at the button progression for this one. So you're just going to type in 305, right? And then I'm just going to go straight to Euler's constant. So to access Euler's constant, you have to push the second button in the top left. And then, so the button that we're looking for now, you can see the E of X just right above it. It looks like this. That's a natural log, not that we care right now. I think we'll cover that in 8.5. We'll see. And then you'll see Euler's constant come up, but not only is it Euler's constant, but it now puts you into the exponent function of the calculator, right? Which means that all I got to do now is type in my 2 decimals, right? 0.01, and then you could just say you're going to multiply this. I'm going to use the dot, even though I know it's an X on the calculator. And we're just going to type this. We're going to multiply this by the year, which would have been 45 right there, okay? So this is all happening in the exponent, and since we're done with that, just push equals, and you'll have the answer. See, again, I made a mistake here. I got a number that's bigger than the one we started with. When we said it was decay, right? I forgot to make this a negative value. So the rate, which I probably should have changed up here as well, that's a negative 0.01. So I'm going to go back in and fix that there. That should make that a little bit better. Negative. Oh, okay. That's much better. So I got 194 point, I got 4765862. I'm just going to round this to the nearest hundredth. It didn't tell me to do that. I'm just going to do it. And since this is a word problem, don't forget to label this in grams. That's how many grams would remain after 45 years of whatever this radioactive crap is. Yeah, again, this is what happens when you don't go back and reread stuff. That was my fault. It is decay on this one, which is what caused our rate here to be the negative right there.